Excellent. Let's begin. So today, Peyton pointed out yesterday she couldn't draw pictures, so I'm going to teach her that today. Okay? Really all we're going to do today is draw various lines of force. You can write some of this down if you want. You've heard this speech before, right? You do what you need to do. They'll be posted later. There's only 6 slides, and that was one of them. So, we've already seen, we only got 5 left. We've already seen that electrically charged objects are able to exert forces of attraction and repulsion on one another without these objects actually being in contact. We call that action at a distance or force at a distance. The concept of force field, because the object is in contact with the field. Peyton?
I just want to point out that you really need to color your slides.
I need to color them.
You need to pick the style.
You need to pick a style.
At the, like click design, and they give you a whole bunch of styles.
Oh yeah, and just stick with it?
Stick with it.
People hate Comic Sans, don't they?
People love Comic Sans.
You do calligraphy.
I can't.
Wingdings.
Okay.
Wingdings 3.
Okay.
I want to point it out.
Thank you, Peyton. I will take that under advisement. The notion of electric field is used by science to describe how charged objects are able to exert force on one another from a distance. Again, review. It's similar to the idea that the Earth's gravitational field is responsible for exerting an attractive force on objects near the Earth. An electric field is thus defined, and we've had to define this in our outline there, as a region of influence around a charged object and can be made visible when small objects like grass seeds or pepper grains are placed near an electrically charged object. And then we get into that discussion where I like to say it's not really there, but it is. Can you explain that back to me, do you think? Yet? Are you ready for that?
It fell on the ground.
Well, without the sound and the force stuff, yeah. Is the field really there?
Yeah.
Yes, but is it physically there? Are there actual molecules or lines or something physically there? No. It's invisible, but it's there, exactly.
A bunch of people at university thought they found the gravity particle.
Oh, yeah?
Call it gravity.
Cool.
So I feel like the molecules in there are wearing like invisibility cloaks because they're actually.
Yes.
So gravity has a particle.
Gravity has a particle. Wow. That's cool. I haven't heard that. Okay, so if you want to draw these, you probably could. If you want to just watch, that's fine. It's not really that hard. It says, sketching the appearance of the electric field in the following cases. In fact, is it the same as this? It is! Oh, Mr. Bennett. Let me just check that this is the same as this. Oh, no, it's not. It's not. Okay. I won't have this up just yet. Okay, so if I've got a single positive charge here, what does the electric field look like? The arrows are outward. Do we know how strong it is? It does depend on how close they are. What if I were to give you a question that said, here's an electric field, like that. Draw me what a stronger field would look like. What would you do? You just add more lines, exactly. You would probably do something like this. I meant a different color, perhaps. Well, I'll do it this time. I'll say, make it stronger. Right? You would simply add more lines. Right?
You're teaching us how to draw. Flowers.
You like that? Why are the arrows pointing outwards? Because a positive test charge would go outwards. Are these, and actually, technically, what should I have done? I should have drawn arrows, but I should have actually done the exact infinity arrows. That's a good way of putting it. I never thought of that.
Is that like mandatory?
Is that mandatory? Like, would I expect that?
Not really.
Probably not. Although, well, maybe I should though. Maybe I should make that a requirement. Because you certainly need to understand that it extends forever.
That's what the arrowhead means, though.
Yeah.
That's true.
If you ever do a graph and
You're right.
arrowhead means it just
You're
keeps
right.
going.
That's a good point. But the arrowhead on a vector doesn't mean that, right? Yeah.
Right.
These are not vectors. True enough.
So you don't need it.
Is it really like there's only a positive and negative particle in the whole universe that they eventually attract each other?
Yeah, of course. Yeah. Well, if they were free to move, right? Yeah. These are all sort of assuming that they're locked in place somehow. Okay, what if you've got a positive and a negative particle? Then, yeah, all of the lines sort of over on the right here would go like this, right? And these ones would be curved.
Why would they be curved?
Well, because if I put a positive test charge right there, it would get repelled, but it would also be attracted, right? It wouldn't just be, there's going to have to be, the electric field exists everywhere. So there would be electric field over here, which I would expect, and you should also have lines like in here as well, right? And really, I don't get too excited about how close they are on something like this. I just care, have you got the arrows pointing in the right direction, and is the shape generally close to what I'm expecting? Okay? So like, don't freak out if, oh, these are 3 millimeters apart, but these are 4. Ooh. I'm not going to get that excited, okay? Are we good with that? Yeah? Okay, what if it's a positive and a positive? What would it look like? Yeah, these would all be away, right? And what would happen in the middle there? Would there be nothing?
No, they just be pushing against.
Yeah, they'd be pushing against each other, right? Kind of like that. Is that what you meant, Ryan? Exactly. There would be a region in here that would be kind of blank. What would that kind of mean? What would that mean, I guess? If there's empty space, that means they're not very dense, and so the field is actually weak. But it would eventually get into a region, if this was a positive test charge, it would eventually get pushed out here, and then it would, because it's dense, it would actually accelerate, wouldn't it? Right? Because it would be into a region where it's stronger. Would it not?
Yeah.
Again, I'm more concerned with just sort of the shape and the look of that. Okay, so on the right here, I've got a positive charge thing, and I've got what I call a negative charge plate. It's like a steel plate that's negatively charged, and it's all spread out. What would that look like? Again, it's always from positive to negative, right?
Yeah.
Would that be all that you'd have to draw, do you think? There would be some out here. And what would the other side of the plate look like? Towards it, exactly. And those would generally be parallel or equidistant apart, and they would be sort of like, that would be equal strength territory, right?
So positive always goes towards the negative?
Yep. It's always the direction. If you were to bring in a positive test charge, where would it go? That's the test, right? Where would it go? What do you think about a positive and a negative plate side by side? Parallel, Steve?
Yeah.
Equidistant, exactly. Where do you think it would be stronger? Would it be stronger inside or out here, do you think? Or would it be the same? And to be perfectly honest, I'm not 100% sure of my answer, but I'm going to see what you guys think. In the middle what? In the middle what? Just in the middle. Would it be stronger or weaker in the middle? Or would it be the same as what it is outside, out here?
Stronger in the middle.
Why do you say so, Steve?
This one was one of the options, and I don't know, it seems like
Who wants to agree with him? Go ahead.
seems like it would work.
What do you think, Keelan? Why should it be stronger in the middle?
Because there's two plates, like, so you're in close to the field.
Yeah, there's two fields kind of added together, exactly, right? That's I would guess as well, right? These guys are going to be towards, right? I'm going to check on that, but I think that's what you should have. So it should be stronger in the middle, and then a little wider out here, right? And there would be some out here as well. Or there would actually probably be some that would be kind of curved like this too. Something like that. Let me think about that. So it's because small objects seem to line up along certain lines that electric fields are often described by drawing electric lines of force as we've done above. It is simply way back to September, our very first unit, a scientific model. It's a physical representation of what we're trying to describe, and we can't really do it without drawing something. That's really what it is. Does that make sense? Is that the last slide? I think it is. Okay, so I have a handout here. It says draw the electric lines of force. On the front, you are to draw them. There's a few ones that are the same, and there's a few that are different. And on the back, there's like an old matching one. This worksheet on the back is so old, I did it in high school.
Oh.
It was originally on papyrus, I believe.
Mr. Bennett, isn't this?
Alrighty, so let's have a look at these drawings here. Can I safely assume that A and B are fine? You want me just to do them all?
Yeah.
You're just saying that because you wanted to waste the time here.
I don't really know. I just want to make sure you're right.
Alright. Positive, negative, right? So it's going to be like that kind of thing, right?
That's B, right?
Away, away, away. Oh, that's B. Yeah, sorry. I thought that was the first one. That one's B. So A is positive, positive. So it's going to be away, away, away. I'm doing it pretty messy, but you get the point, right? Okay. Positive, positive plate. So it's going to be away, 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 and then what's going to be here?
Curved away.
Yeah, away, 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 over here, a ways, right? Not really that hard at all. Positive and negative. Away, 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 towards. Towards, towards. Yeah?
On the sides.
Yeah, probably would be a little bit something there. Positive, positive plate.
Curved away.
Right? So this would all be a ways. Is it important that you have the arrowheads on?
Yes.
Absolutely, right? I can't tell if you know what you're talking about if you don't have the arrowheads. So yes, important. Positive, negative. Towards. Away, 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 away. A little bit of curve there. Something like that. Now, what do you think when it's sort of on the perpendicular thing, kind of like that? Just guess.
I guess. I'm going straight from the top.
Well, they're all negative, so everything's going to be going towards it, right? So like towards. What about in here?
Curved away.
Well, for sure, let's just go over here, right? And over here. So what would a positive set charge do right there? Well, it would go like that, and then it might, right, depending on the strength, it would likely depend a lot on how much charge there was here compared to there, right? Which one has more arrows pointing towards it? But regardless, there would be sort of a dead spot in there, wouldn't it?
Well, it's kind of hard to draw that.
It is. Yeah. You don't draw anything. Positive and negative. Right? So away, 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 towards. Now, I have to warn you, of all the questions, like say there's 8 of these on the test, if you get your positives and negatives backwards, what's going to happen? You're pretty much going to get them all wrong, right? I mean, unless I see that you've got them all completely backwards, I might say, okay, well, I'm thinking that they've got these backwards, and I might have a little discussion with you, and we might be able to come up with some kind of agreement. But really, if you screw up that positive and negative, it's going to be pretty tough, right? Having said that, if you get them right, well, they're pretty darn easy, right? So it's kind of a, 100% or 0, really, isn't it? Okay, what about the matching ones on the back? The ones from way back in 1983 or something like that. One is B-A-A-B. I hear all this crazy talk.
Yeah. B-A-A-B-A-B.
I have.
A-B.
I'm standing over here next to the mic so people can hear me if they're away. B-A.
Yes.
B-A.
No.
What?
I have BA for 3.
B-A, B-A, A-B, B-A, A-B. What I really need to do is I need to mix these up so that it's not just A or B, right? You have to, yes. I really need to get some kid to redraw these and do that for me. Okay, so what I'd like you to do now is I've given you a couple of handouts about Millikan.
Redraw them.
You're the jar, baby.
I've given you a couple of handouts about Millikan. I'd like to talk to you a little bit about that. You guys can use these handouts basically as extra research. These come from a couple textbooks, just a couple pages that I copied. I'm allowed to do that. Copyright lets me copy a couple pages or two. You'll notice that the first one, which has the Millikan's oil drop experiment on the top, there's a nice picture there. I expect some sort of picture similar to this on your video. Okay, this basically explains it, so if you're having some trouble finding stuff online, this can help you out about that. The second one explains again, and there are some example problems. That will be Monday's job to talk about example problems. Okay? You should by now, Peyton, okay, you should by now have some general understanding of what exactly it was that Millikan was trying to do. What was he trying to do? Find the charge on a single teeny tiny itsy bitsy teeny weeny electron.
Why didn't you just Google it?
Good question. Hello, Mr. Hoole. Give me like 30 seconds. Give me 30 seconds and I'm done with these guys. Okay? So yes, Millikan was trying to find the single charge on electron. Do you remember what that charge is? Or do you know what it is? It's on the sheet, by the way, that is handed.
Negative 1.6 times 10 to the minus 19.
Yes, negative 1.6 times 10 to the minus 19 coulombs. It's extremely small. Yes, Randy. Yeah, it's actually 1.602, I think, is the current modern one. We just go 1.6 because the O2 is negligible, right? I think he found 1.6. Something like that, yeah, right. It's really so small that it's, negligible. Remember, he was doing this experiment like 100 years ago, right? So obviously, as Jake pointed out, he just couldn't Google it, right? Like, I mean, he had fairly rudimentary equipment to be doing it, right? It's pretty amazing, actually, that he did it 100 years ago. Come up with the charge on a single electron. That, by the way, is what I refer to as an ELCH. And you may hear me talking about ELCHs. ELCH stands for elementary charge. In chemistry, what is an element?
The things on the periodic table.
Yeah, it's one of the things on the periodic table, but what does it mean? Like if you've got a bunch of, hydrogen, what does that mean? Like what about those atoms?
How many like protons and neutrons?
Like it's a building block, right? You can't get, hydrogen is hydrogen. It's what it is, right? You can't break it down anymore. And you can, but only into protons and neutrons, right? It's elementary. It is a building block. So what does elementary charge mean? Same idea. It can't be broken down anymore, right? You can't have like a milli-ELCH. You know, like we have meters, right? And centimeters and millimeters. You can't have milli-ELCHs. You can't get any smaller than an ELCH. It is the lowest common denominator. Elementary charge. You may now ask your question.
Okay. How much more do you have to learn
Lots.
just before the exam?
Oh, I thought you meant in life.
No, in his class before the exam.
Well, 2 weeks worth. Was there 2 weeks left?
It's
There a
good to
review
draw
period?
field lines.
Yeah, I can handle that.
A little bit more, Kate.